Hey all, welcome to Share Trek. This is your host Raj. Friends, today's topic is about a new discovery about the HIV virus that further improves our ability to design cures and prophylactics. But before we proceed, I want to share an epiphany I had thanks to a subscriber and friend of the channel. I routinely communicate over email and Zoom with select subscribers who I think are serious about making a difference. One such subscriber, Ivan, mentioned to me over email that our topics are very serious and there needs to be some levity. So far, I have complimented myself for being able to consistently study and post HIV-related videos here, along with my main passion, that is investing in gene therapy and AI companies in the original Share Trek channel. Now that we are becoming a bigger channel, I have resolved to improve my approach and add a bit of levity where possible. HIV as a topic remains a difficult one to handle, but I believe I need to empathize more with the viewers and make each video an experience that gives knowledge without making it a daunting or depressing experience. I'll try my best, starting with this video today. I also like to extend a big welcome to the over 2,000 new subscribers who joined us in the last 4 days. I hope our multi-language subtitles are helpful to you. Welcome to Share Trek Global HIV. With that said, let's get started. Welcome back, friends. Picture this. HIV, the exclusive party crasher of the cellular world, slyly slipping past the bouncers. In this case, the formidable nucleopore complex, or NPC, is the bouncer. It's like trying to understand how a ninja sneaks into a party without anyone noticing. Approximately 1 million people worldwide catch the virus's groove each year, prompting researchers like Dirk Gerlich and Thomas Schwartz to unravel the mystery behind HIV's slick moves at the Max Planck Institute for Multidisciplinary Sciences and MIT respectively. Nucleopore complex, or NPC. Now let us meet our bouncer, the NPC. The NPC is an intricate structure spanning the nuclear envelope, acts as a selective barrier controlling the passage of molecules between nucleus and cytoplasm. This central channel, equipped with thousands of nuclear pores, is typically a tightly regulated gateway. However, the HIV capsid faces a substantial challenge. It's over 1,000 times larger than the prescribed size limit of the NPC's diffusion barrier. This means our bouncer, the NPC, can clearly see the HIV capsid. So how does HIV enter the cell? I'm referring to 2 articles and have provided the links in the description. You can check it out for yourself. The first article highlights the paradox of the intact HIV capsid being significantly larger than the nuclear pore size limit. The central pore channel, crucial for transport, is composed of intrinsically disordered nucleoporin domains enriched in phenylalanine glycine, or P or FG dipeptides, and this FG-rich barrier poses a formidable challenge for entities larger than the size limit, but the HIV capsid has ingeniously evolved. In a fascinating evolutionary twist, the HIV capsid has developed an importin-like surface. This structural adaptation allows the capsid to interact with FG motifs from nucleoporins, mimicking the behavior of cellular importins. The second article provides insight into the importin-like structure, revealing how it enables the HIV capsid to slide through the FG phase of the nuclear pore. This adaptation is crucial considering the capsid's width of about 60 nanometers, perilously close to the 40 to 60 nanometer width of the central pore channel. Importins are proteins responsible for importing molecules into the cell nucleus. They recognize and bind to specific signals known as nuclear localization signals, or NLS, on cargo molecules. Importins then guide these cargo molecules through the nuclear pore complex, facilitating their entry into the nucleus. This evolved importin-like surface of HIV capsid effectively transformed the HIV capsid into a molecular transporter. This adaptation serves a dual purpose. It facilitates the capsid's passage through the nuclear pore, and perhaps more critically, it conceals the viral genome from antiviral sensors in the cytoplasm of the cell. The capsid encapsulating its cargo completely, avoids recognition and destruction as it smuggles the genetic material through the cellular virus defense system. So you ask, Raj, what does this mean and why should we care? Well, the revelation of HIV capsid's importin-like surface opens new avenues for understanding viral entry into the nucleus. While many questions remain, such as the disintegration process of the capsid, this discovery holds potential implications for advancing AIDS therapies and prophylaxis. Understanding the intricacies of viral transport mechanisms may pave the way for targeted interventions, bringing us one step closer to unraveling the mysteries of HIV infection. Now, before we start worrying about CCR5 and CD4 receptors not being the only entry point, let us take a deep breath. The article provided does not explicitly specify the type of cell being discussed in context of HIV infection. The focus is primarily on the molecular mechanisms of how HIV capsid interacts with the nuclear pore complex, enabling the virus to enter the cell nucleus, while CD4 T cells, macrophages, and dendritic cell are primary targets for HIV infection. The virus can also interact with and potentially infect other cell types. Some studies and evidence suggest that HIV may have the ability to interact with cells beyond the classical targets. However, the efficiency of the replication and the ability to establish a productive infection may vary among different cell types. Research has indicated that cells such as monocytes, microglial cells, and certain epithelial cells may express receptors that allow HIV to attach and enter. Additionally, there is ongoing investigation into the potential role of cells in the gastrointestinal tract and other tissues as reservoirs for HIV. It's important to note that while HIV can potentially interact with a variety of cell types, not all interactions lead to productive infection. And the virus often faces restrictions at various steps in different cell types. So CD4 T cells, macrophages, and dendritic cells remain the primary targets due to the expression of specific receptors that facilitate HIV entry and replication. The understanding of HIV tropism and its interaction with different cell types continues to evolve as research progresses. Well, this brings me to an end of today's topic, and I realized that I started with levity and in the first section, but soon after that I forgot to keep it light. If you liked this video, please check out the playlist section of the channel where you can find many English HIV videos that I created in the past in our original home. Also, in case you haven't subscribed, please subscribe, and if you wish, you can join our Patreon or YouTube membership program to help the channel. Links are in the description. I hope you have a great day. Bye for now. I'll catch up with you in the next video. See you later.